Okay, welcome Celeste. All right, I'm gonna introduce things a bit. Hold on, let me share my slides. Okay, can everyone see this?
Yes.
Okay, great.
But it's not in the presentation mode yet? Yes.
Okay. All right. Welcome everyone again to Neuro-Symbolic Wednesdays. So if you haven't seen this, these are all the different ways to join. Different ways to work with us. And these are a number of areas we're working in at the moment. You see, by the way, agents, neurosymbolic agents. All right, including some kind of protocol we're working on. So maybe Celeste, we can chat at some point after the presentation. And for the brave who would want to present to help the community, classic papers and in general just older papers. Many ways to get involved. We're hiring and helping startups, and always can use volunteers and donors. We're again starting to use our new, more compact format. All right, so it'll be 60 total. Presentation is 30 or so. And then another 30 minutes on Discord, if you can, Celeste, afterward, after the formal presentation. Just a reminder, the summer school is not that far away, August 6th and 7th. And here's how you sign up. I'm gonna leave this up. You can enjoy Joe's art on the right here. All right, check this out. Put this on your calendar. More importantly, sign up. It'll remind you. And now on to Celeste. We'll talk about sequential decision-making, neurosymbolic style. And just here's her info. So you're coming to us from Italy right now, right, Celeste?
Yes, I'm in Italy.
All right. So, reminder, this event is global, so we welcome folks from all over the world. And here you can find papers that she's going to cover and more about her work on her website. We'll send out these slides. But I'll leave this up so you can take a picture if you want. Okay, and as usual, you can join in one of three places, or any of three places. Heads up about next week, Florentina will present on enhancing constraint programming. And now take it away, Celeste.
All right. So just to confirm that you can see the slides.
Yes.
Perfect. All right. So thank you, Alex, for the introduction. And as Alex already said, what I will be talking about today is how we can leverage symbolic knowledge, specifically in the sense of symbolic policies, to enhance the either solving or training process of sequential autonomous agents. So the idea is that giving a simple task like this, it's pretty easy to solve this kind of task, right? And also it will be pretty easy to transfer the trained agent that solved the first task to solve the second task, like in this case. So this is a simple rock sample task. So basically the agent has to sample rocks in the environment moving through the grid, and he should sample just the good rocks, which are the rocks marked in green. And he should avoid sampling the red rocks marked in red. So the idea is that it's pretty easy to transfer the policy from these two tasks, for example, but it will be quite hard to employ the same trained policy to solve the same task in the moment in which we, for example, move to bigger environments or change the shape of the observation, just like in this case. So it's pretty easy, though, to understand that between these tasks, there's some common knowledge that the agent should exploit and should be able to transfer across different tasks. So the idea today is that I will show how we can extract this symbolic knowledge and possibly use this symbolic knowledge in order to speed up the training process or the solving process in different instances of the same task that we didn't see already. So this is the main idea behind the talk that I will give today, and we will go through 4 different phases in solving these kind of tasks. So first of all, we need to represent the environment in which we reason in terms of either planning or reinforcement learning through a high-level representation that allows us to reason in terms of symbolic knowledge. We will use ASP in this case. So what we want to do is map the standard MDP representation into an ASP representation, and then leverage this representation in order to build an inductive logic programming task that allows us to extract the policy that the agent is using in solving instances of these simple tasks. So once we've got this knowledge, we can actually reason over this symbolic representation of the policy in order to gain suggestions about how the agent is acting in the environment according to different states. Once we've got, again, these suggestions, we can use them either in planning or reinforcement learning in order to speed up the solving process and gain a more efficient solving of new instances of the task that we already know how to solve. So moving to the first step, so to the ASP representation of the MDP, so of the basic standard representation in terms of reinforcement learning. Let's see, first of all, how an MDP works. So basically, what we want to do is representing our agent in terms of what our neural network or our solving process can reason about. So we've got, again, in the rock sample domain, a set of states, which in this case are represented through the different positions of the rocks and the agents and the different values of the rocks. We've got a set of actions that the agent can accomplish. So in this case, moving towards the grid, sampling rocks, checking the value of the rocks. We've got observations in the case the task is partially observable, as in this case. So an observation is the portion of the state that the agent can actually perceive in the environment. We then got transition functions, observation functions, and reward functions that tells us how the environment evolves in the moment in which the agent interacts with the environment. What's important is that since the task is partially observable, the agent doesn't perceive the whole state, so he has to build a belief over the states in which it currently finds itself. So when the agent receives an observation, what it does is building a probability distribution over the possible states that tells it in which state it should be. So once we've got this representation, what you want to do is map all the informations that are useful in our case to a higher level representation. We choose the answer set programming formalism, but any other high level formalism would work the same. What we're interested in mapping between the MDP and the SP formalism are the set of, not the states in this case, but the observations and the belief of the agent. So basically, all the instruments that the agent has to reason over the environment, and also the set of actions that the agent can accomplish in the environment. We want to map that respectively to a set of features that tells us how we should describe the environment and the states in our high-level representation, and a set of actions that should possibly be a one-to-one mapping with the agent's actions. This because we need to go back from the set of actions in ASP to the set of action in MDP terms in order to actually apply the suggestions that our symbolic policy gives us. Right, so in our case, for example, the observation that the agent gains from the environment is its own position together with the rock position. What he doesn't know is the value of the rocks, but he can build a belief over these values, checking the value of the rocks in the environment and updating its belief over the value of the rocks with a more precise observation according to how close it is to the rocks. So how can we map this feature in ASP terms? We can, for example, define features such as the distance between the agent and the rocks, distance with respect to the axis, of course, and also the guess that the agent has over the value of the rock. We choose in this case to sample the guess value, which should be a percentage between 0 and 100 each 10 steps. So this could be a guess of 10 or 20 or 50 and so on. All right. We then map the actions of the MDP, so the possibility of moving in each direction and the possibility of sampling or checking a rock. So once we've got this mapping, what you want to learn is how we can describe the policy that the agent is following through this high-level representation. So we start from observing a sequence of observation traces that the agent performs in the environment. Of course, we're talking about a trained agent in a small instances of the environment, and we want to use these traces in order to build an inductive logic programming task that allows us to extract this knowledge about how the agent is acting in the environment. So again, using the example, how we define an inductive logic programming task. So first of all, we need some background knowledge, which is indicated by B in this case, that tells us what we know of the environment and what is stable in our environment and doesn't change during the execution. So for example, the dimension of the grid, the position of the rocks, well, and that's it in this case. We then want to build a search space, which is S in our example. We go back to this later, but this is basically the set of all the possible actions that we want to learn from. And then we've got a set of examples, where each example is determined by an included set, an excluded set, and a context. So we define the context in terms of what the agent observes in the environment. So we basically map the context to the state in which the agent finds itself in a current moment. And then we want to add to the included set all the actions that the agent performs in that particular state, while we want to add to the excluded set all the actions that hasn't been performed in the current state. So if for this simple example, at the first time step, we would like to add to the included set the fact that the agent is going north, and then so on. On the third time step, for example, we want to add to the included set the fact that the agent is going west, and we want to exclude all the other actions. So what if we want to make this representation a bit more informative? So for example, let's say that we want to somehow encode the fact that the agent actually goes north for 2 time steps instead of 1. So we can combine this representation with the event calculus theory in order to represent when an action starts and which are the conditions that make an action continue over time. So once we've got this combined representation, going back to our set of state action pairs that form our execution traces, what we want is basically build each example so that we add to the included set either the fact that an action starts being performed or continues being performed. And again, we want to add to the excluded set all the other actions that hasn't been performed by the agent. So back to our execution trace. From this execution trace of the small example, for example, we can build all these examples. So at time step 1, we add to our set of examples the fact that the agent starts moving north and not in all the other directions, given the context in which the agent is acting. At time step 2, we want to add to the included set the fact that the agent continues moving north and not in all the other directions, and so on. So once we got this learning task, sorry, what we want to obtain by solving the learning task is basically a set of actions in the form of normal rules. So we've got a conjunction of atoms, which are taken from our context, that imply actions, again, taken from our ISP representation. More formally, this means that we want to generate an answer set that includes all the examples that we included in the included set, and we want to exclude all the examples that we added to the excluded set. To this aim, we employ the IRASP solver, which would return a theory like the one we see here on the screen. So, for example, we can see that the agent should start moving north or south when basically there's a good rock in that directions. So we see that the gas of the rock must be higher than 60, and it should continue moving in that direction as long as it finds itself on the same axis of the given rock. So, cool thing about the IRASP solver is that it also returns the example coverage over the theory. So basically, we've got a measure of how many examples our symbolic theory covers over the given set that we gave as an input for the solver. And this will be particularly useful in exploiting the symbolic knowledge. So this basically gives us a measure of how much we trust our symbolic knowledge and how much our symbolic knowledge is precise in representing the policy followed by the agent. So once we've got this representation, we can actually reason over the symbolic policy that we generated. And to this aim, what we do is, again, starting from the observation of the state in which our agent finds itself, we want to map this particular state to the corresponding ASP representation, such as in this case right here. And then once we've got this grounded ASP representation, we want to see which rules of our symbolic policy actually activate given the current state and the current grounding. So in this case, for example, what we've got is suggestions that as the agent, we're not moving north, moving south, actually, but yeah, this is the idea. So given our state representation, what we want to obtain is a policy that tells us which actions are suggested given the current state in which the agent is located. So once we've got these action suggestions, or either atomic actions or actions that last over time, such as in this case, we want to reason over these actions, both in terms of planning, so Monte Carlo Tree Search-based planning in this case, or reinforcement learning. I will go quite quickly in the planning case because I think it's less simple the case. So within the context of partially observable Monte Carlo planning, so the idea is that at each time step, what the solving process does is selecting a node in the tree of all possible states in the execution traces that is the most promising given the current state and current belief and current value function. And it wants to explore how the execution trace will evolve starting from this state, performing different actions in the state. It then simulates the execution traits according to the current value function gain from the starting of the execution, and it backpropagates the values in order to gain an estimation of how good it will be to take this direction instead of another one. So what we want to do in this case is basically leverage our symbolic suggestion in order to suggest which should be the most promising directions to explore during this exploration phase. So what we do is combine our symbolic policy with the transition function of the domain, which is known in the case of POMDP algorithms, and compute a suggested macro actions that tells us which should be the most promising sequence of action to take given the current state. So the idea is that, given again our small example, in this case, our symbolic policy would compute a set of macro actions that tells us that the agent should move north from 2 time steps. So what we do is increase the probability of this sequence of actions to be explored in the exploration phase of the reinforcement learning of the planning algorithm. So what we do is basically give a higher probability to this direction to be taken in the exploration phase of the algorithm. So there's, of course, a higher probability that the agent, in this case, takes action north and explores action north as a promising direction to solving the task. The cool thing is that since we're computing macro action, we don't need to, of course, recompute all the sequences of action at each time step, but we can leverage the whole sequence of action during the solving process. Since what we do is just increasing the probability of these directions to being explored without actually cutting all the other directions, what we introduce is a soft bias that preserves the optimality guarantees of the original algorithm. Moreover, computing macro actions instead of single-step actions allows us, of course, to reduce the execution time of the algorithm. So moving into deep reinforcement learning, which is way more interesting in this context, the idea is basically the same. So what we want to do is take our symbolic policy, observe which are the actions that are suggested given the current states, and try to increase the sample efficiency of our training process, both in the exploration and in the exploitation phase. So what we can do is, again, in the exploration phase, we're talking about epsilon gradient algorithms, so the two phases are fully separable. So in case of the exploration phase, what we want to do, again, is to reshape the probability distribution according to which the agent chooses the most promising action to accomplish in order to give a higher probability to the actions that are suggested by the symbolic policy. In the case of the exploration phase, instead, what we can do to actually push the agent toward the most promising directions is reshaping the Q value outputted by the neural network in order to favor the actions that are suggested by our symbolic policy again. So let's start with the exploration case. So what we do is, as I said, reshape the probability distribution according to which the agent chooses the random action to perform, according to the confidence about the symbolic knowledge. So basically, we assign a weight which corresponds exactly to the confidence over the symbolic policy, to the actions that are suggested to the agent given the current state, and we want to assign the opposite of this probability to the other actions. We then, of course, normalize over the whole set of actions in order to obtain a probability distribution over the over the actions. This again is a soft bias because again we doesn't shield any possible direction and we don't avoid possibly choosing actions that are not suggested by the rules. This allows us not to, of course, obtain any guarantees in this case, since we're approximating the very function, but at least it allows us to keep exploring the whole environment without cutting out any direction. Importantly, we want to weight both the exploration bias and the exploitation bias using epsilon, which decreases during the network. So in the cases of exploitation, what we do is reshaping the key values outputted by the neural network by a symbolic factor related to, again, to our suggested actions, which increases the value of the key values corresponding to actions that are suggested by our symbolic knowledge. As we can see, the symbolic factor that we employ to reshape the key values is again based on W, as it was before, so on the confidence over the symbolic knowledge, but is also based on epsilon that decreases during training. And this allows us to trust the network more and more as long as the training processes and as long as the network actually learns how to act in the environment. So let's see some quick results in the case of deep reinforcement learning. So we tested both the exploration and exploitation integration in the Dorky domain using what we say should be a partial symbolic knowledge, because as you see, it doesn't cover all the possible actions in the environment. So in this case, the agent has to pick up a key from the environment, and the key has to be of the same color as the door in order to actually open the door and reach the goal, which is marked by the green cell in the environment. So we can see that we've got suggestions for the pickup action, for the open action, and for how to reach the goal once the door is unlocked. But we don't have, for example, suggestions about how to reach the keys or to reach the door once the key has been picked up. We tested this environment we tested our integration in the DQN algorithm. So we compare our methodology both with standard DQN and with DQN guided through the world machines built starting from this partial knowledge, which is not how the world machine should work in the first place, but we wanted to keep to start from the same knowledge for all the algorithms. So here are a few results. Importantly, what we do is training the agent, the DQN agent, over the simplest condition possible. In this case, it was the 8x8 map, so the one we see here, with just one key in the environment, which was always of the same color of the door. And then we want to freeze all the parameters of the network and try to transfer this configuration without any retuning in different and more challenging instances of the task. So in this case, the 8x8 map with 2 keys, or the 8x8 map with 4 keys, or the 16x16 map, in order to see how easily our algorithm would allow us to transfer the knowledge without having to retrain the network from scratch. We see that the approach is quite promising, because in all cases, our algorithm gains better performances with respect to both the baselines. So yes, this symbolic knowledge actually allows us to avoid returning from scratch the algorithm when changing the map and the configuration of the environment. We also performed a few ablation studies in order to investigate either the contribution of the two phases of our algorithm, or the different values for the epsilon parameter and the confidence parameter. So we see that both the phases of our algorithm actually contribute to the solving process, but the combination of the two phases, so the whole algorithm is the one that performs better with respect to the other one, of course. We also see that different values of epsilon actually change the way in which the algorithm performs. So there's a bit of tuning regarding the epsilon parameter that should be done to gain the best advantage in our methodology. And we also see that setting the confidence value to a value that isn't the one actually that corresponds to the confidence over the symbolic policy actually decreases the performances of the algorithm as it should be. So to conclude, what I showed you was basically how to extract and leverage symbolic policies in the context of sequential decision making in order to enhance the performances of both the solving and training processes of autonomous agents. So yeah, I think this is quite a promising direction, and I'll be happy to discuss it with you and to answer questions.
All right, great. Thank you so much, Celeste. Very
Thank
nice
you.
work. Let's see, you've done a lot on this thread, so I really I love this stuff. I want to take a look at it myself. Questions from the audience?
1 second. I don't think we have questions so far. I have a couple of questions myself.
Okay.
So Celeste, maybe you can summarize in a couple of sentences what are the key differences between like standard reinforcement learning and your approach? What is the intuition? What like new idea you bring versus other approaches?
Sorry, between standard reinforcement learning
and what you suggest?
Oh, okay. So the idea is that when training a reinforcement learning agent, you're of course bounded with respect to the input of the network. So as we saw, for example, in the rock sample case, if you change the observation window, the size of the grid, the number of rocks, you should actually retrain the agent in order to adapt to the new observation. Which is actually, of course, not efficient, especially in the case in which the strategy to solve the task is the same, right? So what we want to do is extracting the strategy in order to use it to speed up the training processes when it has to be repeated from scratch.
Thank you.
So
And another question I have is, what is manual in your approach? You showed like several steps. In particular, I'm interested when you showed this mapping to ASP. Do you do this mapping manually?
Yes, you should perform the mapping manually. Of course, we try to stick to exactly what the agent can perceive of the environment in order to avoid, adding extra knowledge or extra information to the training process. So the more you stick to the state and the observation of the agent, the more you're precise in your knowledge.
So it looks like this step, it will be different for different problems, right?
Yeah, of course. You have to redo the mapping when you switch to different problems.
And anything else which is manual in the whole process, or just this step?
No, nothing except for this. Well, of course, you have to tune the parameters as in standard reinforcement learning, but once you do that, then everything.
Thank you very much. And we received a few questions from audience.
Sure.
The first question is, the knowledge captured in ASP should be as minimal as possible. How is it ensured?
Yeah, sure. So the ILOSP solver actually guarantees that if a solution is found, is the minimal one. So this comes for free using this solver in particular. We don't necessarily need the ASP theory to be minimal, but of course, the bigger it is, the more the computational weight is. So we want to keep it minimal.
Okay, thank you. The next question is, can you give some examples of what the symbolic policy looks like in the key door domain?
Sure. So let me share the screen again because we actually have the symbolic policy in the slide. So here it is. So this is the symbolic policy that we are using in this case. So you've got rules that basically tells you that the agent should pick up a key if the key is of the same color as the door. You've got rules saying that the agent should open a door once it is carrying the key of the right color, and it should go to the goal once the door is unlocked. So yeah, this is our symbolic knowledge for the door key domain.
Thank you. One more question we currently have is, has there been experiments on large domains? For example, 100 by 100 grids, and what are the results?
We didn't test such large environments. We already had to manually change the definition of the benchmark in order to test multiple keys in the environment, because standard
What was the biggest?
benchmarks are quite small. So yeah, this is the best.
What was the biggest ones that you tested it on?
The ASP reasoning actually doesn't bring a significant overload in terms of computation, right? Because the set of predicates remains quite small, even if scaling to larger grids, especially if you keep the observation window the same size, right? So yeah, the performances will probably be, I hope, better than the standard reinforcement learning algorithms. I can't quantify how better, but
And also, I'm curious, what is the compute that you use? Like, did you do it on your local MacBook? I don't know. And how long does it take for the problems that you showed?
you mean extracting the symbolic knowledge or doing
I mean the whole process. The whole process.
Oh, okay. So extracting the symbolic knowledge is actually the most heavy part in terms of computation, because it's basically SAT solving. So it really depends on the number of samples, the number of predicates that you add to the search space. So that's the heavy part. Once you've got the symbolic policy, we tested. So the biggest increment that we had in the training process was about 5 seconds over 3 hours of training, I think. So definitely, not a big improvement.
Okay, thank you.
Thank you.
Another question: what are the limitations currently of this work?
I would say the current limitation is probably in defining the mapping, because from that depends all the accuracy of your theory and how well the symbolic policy performs over the solving process, right? So the limitation is that the mapping has to be done by hand, and yeah, you have to trust
Do you,
this map, of course.
do you mean the mapping from the domain to logic?
Yeah, from the NDP to ASP. That's the current bottleneck, I'd say.
Are you planning on extending this work, do you see any further directions that maybe you personally are working on, or people who may be interested can work on?
So this question of mapping is, of course, one of the main open problems. What we already done is extending the same procedure to different deeper algorithms. So, for example, in the distributional case or in the actor-critic algorithms. So these are two extensions that we already submitted, actually. So yeah, we are waiting for the results on that.
Okay, these are all the questions from audience. Alex, do you have any questions from your end?
Yeah, I guess when you, so I think that's a big thing, not needing to retune for new problems. So this is a, leveraging both the transferred knowledge and the power of reasoning in general to essentially be able to do out of distribution generalization. But can you show again the, maybe you did already, but the transferred knowledge, what that looks like?
Yeah, sure. So this is the knowledge we transfer for the Turkey domain. You should see that, I think.
Oh, okay. You just mean the policy. But
Yeah.
does it learn predicates in this setup?
These are learned not from us. These are learned from a previous work from Look the Riot. They actually use a planning technique to learn this policy. But yeah, same. The application then is the same.
And what did you mean by minimal knowledge when you said it will find a minimum knowledge?
Yeah, if you use ILASP to learn the symbolic policy, then ILASP ensures that you find the minimal ESP representation. So basically, the shortest rules and the less number of rules that you can.
Ah, okay.
Yeah.
You mean the smallest rule set, or do you mean the rule set that gives you the shortest reasoning paths?
No, the smallest rule set.
Okay. And then when you talk about macro actions, what do you mean exactly by macro actions?
So in this case, we limit to macro actions in the sense of actions that actually are performed for multiple time steps. So for example, going north for 3 time steps and then turning west.
Okay.
And so on.
And you're learning macro actions?
Yes, for that work, we're learning macro actions. We would also be interested in learning macro actions in the usual sense, so a sequence of any kind of actions. The limitation in that case will be in defining which are the macro actions in which we are interested in. So yeah, you have to choose that these macro actions should be the ones that should be learned.
Do you
If we
have
start with these repeating actions, then we can basically just see when an action is repeated without performing any choice on that.
Do you have some like hyperparameters for like what micro action could be? Like, I don't know, between 2 and 10 steps or something, or it could be anything.
Well, I think that probably the most immediate way to identify macro actions will be on a statistical basis. So you see which are the sequences of actions that are repeated most during the execution trace. You have to arbitrarily decide, of course, a length for the macro actions. I wouldn't think so. The longer the macro action is, probably the less it is generalizable between different grids or environments, right? So I would probably choose shorter macro actions, let's say.
Okay, thank you. We received one more question from audience. I think the rules should also be small. That is, the preconditions should be minimal so that it will be more transferable. In a sense, you are discovering the core knowledge. It's more like a comment rather than a question. But
I agree. 80% probably. So of course, shorter rules means more generalizable rules. On the other hand, it also means less precise rule, potentially. So yeah, really depends a lot on how you map the MDP into the SP representation. But yeah, you have to find the right balance between a shorter set of rules or shorter rules and how well they describe the environment.
Alex, we have 4 minutes if you have any more questions or comments.
Yeah, just zooming out a bit, I think what we've been seeing is in your work and a few others, looking at the state of the art of neurosymbolic agents. I think what we're showing as a field is, to me, kind of how agents need to be in the future. In particular, human readable policies and the ability to incorporate domain knowledge and so on. But we're not showing yet, and just to set this as clearly as a challenge for us as a field, we need to be able to show these much larger domains. And, I think once we can break through that, then there's no reason neurosymbolic agents should not take over all agents. I mean, it should be the only way to do it. So we should really put as much effort as we can into this scaling problem. It is the thing that I think when people look at our kinds of methods, they go, okay, dismiss. It doesn't scale. So just want to, give that animus to our researchers in this area. Now, and like you said, in this case, it's actually not. I was expecting you to say that a key bottleneck is maybe the computational cost of doing the ASP part, but it isn't, because the domain is small. So it's really the computational cost, in effect, of the ILP, right? Essentially what it boils down to. So the other thing you mentioned, of course, is not just in your work, but in all logic-based approaches, is having to set up the problem in logic in the first place. So I think it's really hard, this problem, but really want to highlight that for folks working in neurosymbolic AI broadly. This is a key bottleneck that must be overcome. Do you have any thoughts on either of those two kind of big problems, Celeste?
Yeah, I think the cool thing of this kind of approaches is that you can actually contain the overload given by ILP by keeping, the ILP solving focused on small tasks, and then transfer the knowledge on bigger instances and scale over bigger instances. So I think this is actually a promising directions for this reason in particular, because it allows you to, again, contain the bottleneck over the small instances, right? So
and how do you do that exactly?
you just collect the learning traces from small instances of the task. So fewer objects, smaller grids, and then if you actually gain some generalizable knowledge, you can apply it to the bigger instances without bringing all the the overload with you, because you already performed the LP reasoning first.
Yeah.
It sounds a little bit like curriculum learning. Isn't it like you give your agent a small task first, a small task or a few, and then kind of hope that the agent can learn those and you can transfer those to bigger problems, something like this?
Yeah, and the idea is the same. Yeah, exactly.
Very good. How about the issue of the domain mapping, as you refer to it?
That's a thing. That's definitely a thing. I mean, I don't see much work in that direction. There should be, I think. We're trying to look at it. So it's not easy. I mean, you have to at least define a set of predicates. So if you want specifically also to keep it explainable in some sense, you need to, establish the meaning of the predicates at least. So yeah, that's definitely an interesting direction. I've seen some works, I guess, in trying to employ visual language models in this sense. So basically observing the state and trying to ground some, semantic concepts from the states. So that's a direction that's being taken, I think. I'm not sure it's the best one, but something at least.
Alex, and we need to end a little bit early today. We just have a couple of minutes left, and we have one more question. So maybe we can just answer last question.
Oh yeah. Okay. Sure. One more question. Yeah.
One more question. I believe you used epsilon greedy DQN as your foundation, but sometimes value-based methods are often sample inefficient. What led you to choose this over a policy-based approach?
We actually tried to train PPO first on this environment, and it performed terribly with respect to DQN. So these are challenging tasks in general for this kind of agents, because you would basically need a memory to solve the task more efficiently. What we wanted to show is how we can increase the performances of the algorithm more than how to solve that specific task efficiently, right? So yeah, this was the idea. But yeah, I agree that DQN is not the best for solving this kind of tasks.
Okay, thank you very much. Alex, we need to wrap up.
Okay. Well, very good. Thank you so much, Celeste.
Thank you.
And everyone, check out her work. And Celeste, if you have time to jump on the Discord,
Yeah, sure.
questions. Otherwise, see y'all next week. We'll have more great stuff. Thanks, everyone.
Thank you. Bye.
Thank you.